Hi guys, today what I want to talk about is what happens when you have projectiles that are moving at very high speed. So projectiles that are moving very, very quickly. So I want to start off as we talk about these rapidly moving, these high velocity projectiles. I want to start out by talking about an experiment that Isaac Newton did. All right, so I'm going to go ahead and switch over to my document camera. And we're going to talk about this is a low-tech lesson again. But I want to talk about what's called a thought experiment that Isaac Newton did. And what Isaac Newton did is he envisioned a cannon that was going to fire a cannonball, and that cannonball is going to travel some distance. Now, if you guys watched the last video, you know that basically the distance that a cannonball is going to fly is partly dependent upon its initial velocity. And so what you would see is, you would see that if I had a certain velocity, I'll just pick a number, let's say that this is 200 meters per second, that it would land in one place, okay? On the other hand, if I fired that the velocity of that projectile was higher, it is actually going to go a little bit further. And so it's going to land over here. If let's say that this was 300 meters per second. And if I fired off that cannon even faster, so it had an even higher velocity, it's going to go further still. And so it'll even go behind this cloud here and land somewhere over here if it was, say, 400 meters per second. So basically, the faster you shoot, the faster that initial velocity is, the further that cannonball is going to be, the range of that cannonball is going to be from where the cannon was. So Newton had a good idea of this. I mean, he had this figured out. He knew that the higher the initial velocity coming out of the cannon, the further it's going to go. All right, so he had that down. But he started to imagine. See, he didn't have a cannon that could really, or nor could he observe a cannon that could have higher and higher and higher velocities to see what would really happen as you got these going quicker and quicker and quicker. So he had to imagine, based upon what happened here, he's seeing the faster that velocity is, the further it goes. Based upon that observation, he starts to imagine, well, what if I could fire that cannonball even faster than I'm capable of doing? Well, if you follow the logic, the faster this is going, the further it goes. So if I fired even faster than this, if I wanted to fire a cannonball at 1,000 meters per second, then it would go even further than this, further than he could actually do. That's why it had to be a thought experiment, because he couldn't actually conduct it. And so what he said is that basically that as the range increased, he could no longer think of the Earth as being a level surface, right? If you look at Earth, if you're down here on the surface and you look out towards the horizon, it looks mostly level. But if I move away from Earth a little bit, so I have a different point of view, I can start to see the curvature of Earth. And so what Newton started thinking was that as he got further and further from Earth, he was going to be in a situation where the surface was no longer flat. All right, the surface is no longer flat. And so he would have had his first measurements, which would have been really tiny. They would have been like this. I mean, the ones that were up above here on the page, I'm going to represent those as a bunch of lines, but they really didn't get too far away. All right, he envisioned that as he looked at a bigger portion of Earth, that instead of being flat, it's going to start to take on the curvature which Earth has. So yes, even in the mid to late 1600s, we knew the Earth was spherical. It's only recently that that people that don't know anything have tried to say that it's flat. So Newton knew that we had a spherical Earth. And he started to think, well, if I start firing faster and faster and faster, I'm going to see that I'm no longer going to be firing over flat ground, but I'm going to be firing over ground that's actually curved. And so what you'll notice, or what he noticed, was that the path that these projectiles would take, which he knew was a parabola, that path starts to look more and more and more like Earth's curvature. So basically the trajectory that the cannonball takes, which is always going to be a parabola, starts to look more and more like the curving surface of Earth. So the faster that we, again, what he's saying here, the faster that we launch each of these projectiles, the further they're going to go. And as they go further, their trajectory, the shape of this motion starts to look more and more like the curvature of Earth. Well, the next thought is just kind of a natural step, I think. The next thought would basically be that if I fired this fast enough, if I could shoot this projectile at a high enough speed, eventually it would have exactly the same shape as the curvature of Earth itself. And so what he basically imagined is, if I kind of take this thought out as far as I can, I'm going to get a situation where if I look at Earth, all right, what he would envision, let me pull back just a wee bit. What he envisioned was that you could get a projectile. Again, I'm going to have those initial shots that look something like this. And as velocity gets higher and higher, it seems to go further and further. But at some point, he would fire this at a speed that was fast enough that that projectile would basically never come down, that it would continue to fly around Earth and never hit the ground. Trying to keep that nice and straight. Eventually, I guess you could say it would come right back and hit him. All right? That trajectory matched Earth's. And we have a name for this. I mean, that cannonball would essentially be in orbit. Okay? So essentially, that projectile goes into orbit around Earth, and it continues to move in that orbit. All right? Now, if you didn't fire it quite fast enough, what you'd find is instead of coming to the same elevation that it left here, it might be a little bit lower. And what would that mean? That would mean eventually it will hit. It's just going to kind of keep going around and getting a little smaller in its orbit each time until it finally hits. Okay? So, I made this word up, projectilism. It's a constant state of projectilism, which basically means it's continuously falling, but never actually hitting the ground. So just like a regular projectile, its gravity's trying to pull it inward. It's just that it's moving so fast that gravity's acceleration is not strong enough to pull it in. So it stays in orbit. Now, Newton, he really didn't have artificial satellites like cannonballs that he could get moving that fast. So really the reason he was doing this thought experiment is he was trying to explain how the moon could stay in orbit around the Earth. So he's trying to explain how the moon stays in orbit. And this is what he comes up with. He basically says the moon must move at a certain speed as it revolves around Earth. It must move at a certain speed that will allow it to stay in orbit. And depending on where you want your orbit to be in terms of being close or further away, that speed's going to vary just a little bit. But in general, he calculated that the speed he would need to stay in orbit would be approximately 7,500 meters per second. That's about how fast that you need to be going to achieve orbit. All right, so orbital speed is right around 7,500 meters per second. So the way to think about this, you guys, is that anytime that you see a satellite, and by the way, I will put a PDF copy of this in case you want to keep this for notes. I'll put a copy of that in your module, okay? So the way to think about your typical satellite that's orbiting around Earth, okay, is that it's essentially just falling. It's like a big square cannonball that we've made it so that it moves fast enough that it's falling in the same parabolic shape, rough orbit, as the Earth's surface itself. And so it maintains the same distance above Earth and moves at that speed that's around 7,500 meters per second. Okay? Meters per second. So this is how orbit works. If you fire something fast enough, if you can throw something fast enough, it actually will go into orbit around the planet that you happen to be on. So the International Space Station, all right, the International Space Station today, it's moving at about that speed as it goes around Earth, all right, about 7,500 meters per second. Okay, so I'm going to show you guys a couple of things really quick. And what I'm going to do is share my screen. Let me go back really quick and find the item I was looking for. There it is. And I will share my screen with you guys. Okay. So here's kind of an example of Newton's experiment. This is an app that I found online. And what you can see is you can kind of play with the velocities here. So for instance, if I want to have a velocity that's 1,000 meters per second, this will show you, if I fire that projectile from this location, it'll show you how far it'll go. So if I click fire, you can see it really didn't go very far. So 1,000 meters per second is nowhere near fast enough to achieve orbit. How about 2,000? Well, it goes a little further from where I started, but not a whole lot. Okay, how about, let's take this up to 4,000. 4,000 meters per second. You can see it goes further still. How about 6? That goes quite a ways if you think of Earth. If I take it to 7,000, you're going to see we're getting close now. And it goes like about a third of the way, maybe a little bit more than a third away around Earth. About 7,100. Oh, that's close. It's close. Yeah, it may even make it there. Now notice that orbit, though, that last one I did, it almost touches the South Pole here if I fired from this position at the top. So that would make kind of an unusual orbit where it was really close at some times, but further away at others. Generally, what the thought is, if you can get this to 75, you know what, let me clear that so it takes off on its own. 7,500 meters. If you look at it, it's a fairly nice, even orbit. I don't see like really, really huge differences between this side and that side. So again, this is simply a product of how fast it's fired and how strong that gravity is pulling in. So if Earth had less gravity pulling down on that projectile, I wouldn't have to fire it so fast. So this is kind of one of my problems. I don't know if you guys have seen the movie, oh shoot, it was the one where there was a comet coming towards Earth. And like Bruce Willis had to go land on the surface. Apocalypse, I can't remember. But they landed on the surface of this comet, and they go running around and they're trying to plant explosives and drill down under the surface to plant these explosives to blow up this comet. Well, one of the things they did is they were running around. They had these little like ATVs, and one jumped over this big chasm. Guys, there's so little gravity on a comet that you might be able to just jump right off the surface yourself. If you started running, the gravity is not enough to really hold on to you, and you could theoretically go into orbit around a comet or an asteroid. It really wouldn't be that hard to do. And again, it's simply a product of gravity and the speed at which an object is moving. Okay. The other thing I would tell you guys while I'm here, I want you to notice something. This is a picture from a SpaceX launch, and what they're launching is a whole series of Starlink satellites. This is going to be Elon Musk wants to provide you with wireless internet worldwide using satellites instead of like telephone towers and things like that. So it'll all be wireless and it'll communicate with satellites. Now, the thing I want you to pay attention to, number one, is this speed. The speed, they're into space now. You can see the curvature of Earth here. They're into space, and they're traveling at 26,773 kilometers per hour. I actually did a conversion on that, and that is right about 7,500 meters per second. And again, it's not for no reason they're traveling at that speed, because all they're going to do with these, and I'll start playing this, turn down the cheesy music. All they're going to do with these satellites is simply release them. They're already traveling at the speed. They're traveling more than 7,500 kilometers, or excuse me, meters per second. And so all they really need to do at this point is simply let them go. Let the satellites go, and they'll be traveling at the speed they need to travel at. So watch for a second here. I'll turn up the volume.
It's going to look a bit different from other separation sequences you've seen, aside from Starlink, of course. But once released from Falcon 9, the satellites will slowly disperse. They might even bump into each other, which is totally okay. They were designed with this in mind.
I want you guys to also notice you're almost 300 kilometers up. 300 kilometers up.
Signal and watch it live.
So they're simply kind of getting in the orbit that they want to release these in. That's what this path is. They're already traveling at the right speed, and they're already pretty much at the right altitude. So they're just going to follow this and let them go. There it goes.
That's all 60 of those Starlink satellites on their merry way.
So you can see it's not like it's jetting away from the rocket. They just kind of let it go.
On the fanning. We didn't catch it this time. We got really close, but we're going to keep on trying again and give you more updates as that continues.
All right, you guys. So I'm going to pause that one. I have one other video that I want you guys to see. And this is one where these guys are in the International Space Station. Now, you might have seen in movies that when astronauts are in outer space, it looks like they're floating, right? They're floating through the air. But if you really understand the way that projectiles work, you realize they're not really floating at all. They're really falling. They're falling. He's making a taco, it looks like here. Looks like the yuckiest taco ever. They're actually falling. Now, why don't they fall to the floor? Everything around them is falling at the same speed that they are. So from their point of view, it doesn't really feel like they're moving at all. But the truth is everything around them is moving at that 7,500 meters per second. So they don't really feel any weight because the floor is moving away from them at the same speed that they are falling towards it, if that makes any sense. Okay, so again, the point you guys should take away from this lesson is that if I can launch a projectile fast enough, the shape of its fall, the parabola that it makes, will match the shape of Earth, and you will just continue to fall around the Earth, never landing, always falling. I have no idea what that stuff is in his spoon. But again, that blob of whatever it is was falling at the same speed. All right, so that's it for this lesson, you guys. This is fast moving projectiles. We will see you next time.